Okay, I'm Yuqiang. Today my topic is about some pitch-based features and their distributions on selected music generation systems. This research, first, it is vital to find an objective evaluation method when we compare different music generation systems. There have been some research on different pitch features about one single melody. For example, the average duration and average velocity as mentioned before. However, it is challenging to select the features that can well describe the system performance in terms of the randomness, cohesiveness, or naturalness. So our research attempts to use several statistic features to objectively evaluate the performance of music generation systems from the perspective of feature distributions. For the future work, we think that these statistical features could be used in problems such as the detection of generated melodies. It's also helpful in providing a clear direction during the training process of different music generation models. For example, we can lead a model to generate music in a specific style. There are some details about our work. First, we do not use any geometric interpretation of the pitch movement, and all we can consider is the interval, which are the delta pitch between each two consecutive notes. The intervals is measured in semitones. And in terms of tonality, we do not follow the strict definition in music theory, but we only consider the common 12 major scales for simplicity. Here are our proposed three statistical features: the interval mean, interval standard deviation, and the tonal standard deviation, which can be seen as three functions that maps a melody to a real number. The first two, the IM and ISD, are easy to understand because we just have to calculate the delta pitch, namely the intervals, and for all these intervals in the melody, we calculate the mean and the standard deviation. These are the IM and ISD. To get the TSD of a melody, we have to count for each of the 12 major scales how many notes in the melody appear in this scale. Then there are 12 counters. These 12 counters are normalized so that they sum up to 1, and the standard deviation is the TSD. So next, in a few slides, we will use some empirically chosen music to demonstrate what these features are describing. For example, interval mean. We think that interval mean can estimate the overall tendency of a melody. For example, for a common traditional song. The IM is near to 0 because we cannot see the overall rising or decreasing tendency from this melody. Another example is obviously this is a rising melody, so its IM is 1.3. It's a positive value. And let's see another example. As you can hear, the melody is a descending line. Therefore, the IM value is a negative number, which is 0.6. Let's move to the internal standard deviation. We think that interval standard deviation can measure the evenness of the melody. By evenness, we mean if the melody is equally smooth everywhere or equally wavy everywhere, then the ISD should be small. For example, for a common tune. This melody line is smooth, so therefore it has a 2.8 ISD. Let's consider another example. Notice that this melody starts to become wavy from the later half of the part. So therefore, its ISD is relatively higher, which is 7.7. And let's see another extreme case. Yes, in this case, all the intervals in this melody is either larger than an octave, which is 12 semitones, or just unison, which is 0 semitones. So the ISD here is high up to 12.6. Finally, let's see the tonal standard deviation. We believe the tonal standard deviation denotes the extent to which the melody has a clear tonal center. For example, the Bach's famous Prelude in C major all the notes in this melody stay in the C major scale, therefore it has a quite clear tonal center. Therefore, the 0.04 is relatively high TSD. Let's consider another example. In this example, there were more chromatic movements, so that by our algorithm or the definition of TSD, there is slightly vague tonal center than the previous one. So therefore, the TSD decreases to 0.04 or 0.024. And another extreme case is if we just randomly generate pitches by the computer, the TSD will be extremely low. For example, this totally random pitch sequence has a quite low TSD. So as we know what the three proposed statistical features describe, now we want to use a data set. We use the CSMT 2020 data challenge data set with a half melody composed by human and another generated by different generation systems. For example, music VAE, MIDI-net, and the music transformer. And according to the labels we have, we calculate all the three statistical pitch features and plot them using the kernel density estimation. And from the graph, we can see the three features vary in the systems or human. Basically, this graph can tell us the following information. The first is that the human compositions, which you can see in the blue curve, has an overall normal distribution or Gaussian distribution because it has only one single peak and it's quite similar to a bell curve. But however, another thing is there are multiple abnormal peaks, as you can see from the other three curves. For example, in the ISD between 18 and 20, there were an abnormal peak that we cannot understand quite well. And for the tonal standard deviation, there are much samples that has quite low TSD. So we can see the clear difference between the human composed melodies and the machine-generated melodies. And the last thing is, among the three music generation systems, music transformer tend to have the closest distribution to human compositions. So here, to conclude, we can give the conclusion that the proposed features can reveal the characteristic of either human compositions or human generation systems. And this is the end of my presentation, and I'll try to answer the questions.